There is a quiet, almost imperceptible shift happening above us, right now, as you watch this. Out in the deep black, far beyond the thin blue line of our atmosphere, a new kind of pioneer is at work. These are not astronauts in pressurized suits, but machines, intelligent, autonomous systems engaged in one of the most profound preparatory acts in human history. They are mapping the heavens. They are the silent cartographers of orbit, and their work is fundamentally reshaping our destiny. For centuries, we have looked up at the moon, at the dusty red point of Mars, at the infinite tapestry of stars, and we have dreamed. We have drawn maps based on what we could see through telescopes, stories based on what we could imagine. But now, for the first time, we are not just dreaming of these places. We are knowing them. We are learning their contours, their composition, their secrets, through the unblinking eyes of robots we sent ahead. This is no longer science fiction. This is a meticulously executed, ongoing reality. Think about that for a moment. Long before the first human bootprint is pressed into the red soil of Mars, that entire world will have been charted, studied, and understood with a precision that rivals our maps of Earth. Every canyon, every mountain, every potential resource and hidden hazard will be catalogued by these silent observers. They are our scouts, our digital Lewis and Clarks, venturing into the ultimate wilderness so that we may follow safely. They operate on their own, making split-second decisions millions of miles from any human controller, using artificial intelligence to interpret alien landscapes we can only picture in our minds. This is the quiet revolution happening overhead, a symphony of data and discovery played out in the vacuum of space, and it is laying the very groundwork for our future as a multi-planetary species. In this video, we are going to journey together into the heart of this breathtaking endeavor. We will uncover how these robotic cartographers see what we cannot, how they think, and how they are tirelessly preparing new worlds for our arrival. We will explore the incredible technology from AI-driven satellites to swarms of tiny probes that is turning the unknown into the known. We will see how this silent mapping is already influencing everything from scientific discovery to the birth of a new space economy. This is the story of how we are building the roads to the stars before we ever take the first step. It's a story of immense ambition, profound innovation, and a future being written in data points and orbital paths, and it's all happening right now, just over our heads. To truly appreciate the silent revolution happening above us, we have to rewind the clock and understand its humble, mechanical beginnings. This story doesn't start with a dramatic countdown or a triumphant landing. It starts with a fundamental, practical problem. How do you land safely on a world you've only ever seen as a distant, blurry sphere? The very first forays into orbital cartography were born from this simple, critical need for situational awareness. Before any human could take a giant leap, a machine had to take a careful look. The earliest lunar orbiters in the 1960s, like the United States Lunar Orbiter program, were our first attempts at this. They were mechanical photographers capturing grainy but revolutionary photographs of the moon's surface. Their primary mission was starkly practical: find smooth, safe landing sites for the Apollo astronauts. They were the pathfinders, their images pored over by teams of scientists who manually analyzed craters and slopes, their work quite literally paving the way for those historic first steps. This initial need for basic safety quickly blossomed into a deeper, more complex ambition. We didn't just need to know where it was safe to land, we needed to understand what we were landing on. What resources were available? What was the geological history? This shift in questions demanded a leap in technology. The true genesis of modern orbital cartography, the moment it moved from simple photography to sophisticated mapping can be traced to missions like NASA's Lunar Reconnaissance Orbiter, or LRO, which launched in 2009. LRO was a game-changer. It wasn't just taking pictures, it was performing a detailed medical scan of the entire lunar surface. Its suite of instruments, including a powerful laser altimeter that fired millions of pulses to measure elevation with pinpoint accuracy, and high-resolution cameras that could see details as small as a desk, allowed it to construct breathtakingly detailed three-dimensional maps. It identified perpetually shadowed craters at the poles that harbor water ice, a crucial resource for future sustainment, and mapped temperature variations with incredible precision. The success of LRO and similar missions did more than just provide data. It revealed a new paradigm. It showed that a single, well-equipped robotic scout could autonomously gather more information in a year than decades of Earth-based observation had provided. This proved the immense value of sending these silent cartographers ahead of us. They are unburdened by life support systems, able to focus solely on observation for years on end, and they can take risks in treacherous terrain where we would never send a human first. The field evolved from a supporting act for human missions into a sophisticated scientific discipline in its own right, a fusion of robotics, artificial intelligence, and remote sensing. The foundational work done at the Moon became the blueprint, a proof of concept that these techniques could be applied anywhere. The quiet hum of machinery mapping our Moon was just the opening note in a symphony that has now expanded to encompass the rust-colored plains of Mars, the rugged terrain of asteroids, and beyond, building an atlas of the solar system one pixel at a time. But the sheer volume of data these missions collect is so immense that traditional human analysis simply can't keep pace. This is where the true magic happens, where artificial intelligence steps in to become the indispensable brain of the entire operation. Think of it this way: a single high-resolution mapping satellite can beam back terabytes of information every day, enough data to fill thousands of feature-length movies. For a human team to sift through that, looking for a specific mineral signature or a single safe landing zone the size of a parking lot, would be like trying to find one particular grain of sand on an entire beach by hand. It would take years. Artificial intelligence, however, can process and analyze that same colossal dataset in a matter of hours, identifying patterns and details that would be completely invisible to the human eye. It's the difference between having a single, powerful flashlight to explore a dark cave and suddenly flipping on a stadium's worth of lights to see every single detail at once. These AI systems are far more than just fast number crunchers. They are sophisticated partners in discovery. They employ complex algorithms trained on vast libraries of geological and topographical data. An AI can look at an image of a Martian cliff face and not only map its shape but also analyze the subtle color variations in the rock to hypothesize its mineral composition. It can cross-reference that with LIDAR topography to assess the slope's stability, and then with historical weather data to predict its erosion rate. This ability to fuse different types of data, visual, spectral, thermal, is what transforms a simple photograph into a rich, multi-layered map teeming with actionable intelligence. The system isn't just showing us a picture of a crater. It's telling us that the crater's floor is flat, likely composed of basaltic rock, receives ample sunlight for solar power, and may contain subsurface water ice based on temperature anomalies. It's providing a full risk assessment and resource report without a single human ever looking at the raw data. Perhaps the most revolutionary aspect of this AI-driven cartography is its capacity to learn and improve entirely on its own. Through machine learning, every new image it analyzes, every new terrain it maps, makes it smarter for the next mission. If an algorithm initially misidentifies a certain type of dust cloud, it can learn from that mistake, refining its model so it doesn't happen again. This means that the maps being created for, say, the fifth mission to a specific asteroid are orders of magnitude more accurate and insightful than the maps made for the first. The AI adapts to the unique quirks of each new environment, the strange weather of Titan, the intense radiation around Jupiter, the delicate, low-gravity rubble piles of asteroids, becoming a specialized expert for each world it encounters. This continuous, automated improvement cycle creates a living, breathing atlas of the solar system that gets smarter and more detailed with every passing day. This level of intelligence grants these robotic cartographers a stunning degree of autonomy, which is absolutely essential when they are operating light minutes away from Earth. A probe orbiting Mars can't call home for instructions if it encounters a sudden dust storm that obscures its view. The communication delay means that by the time its help signal reached Earth and a response got back, the opportunity or the danger would have long passed. Instead, the AI on board can make real-time decisions. It can recognize the storm, calculate its probable path, and autonomously reprogram its own survey schedule to focus on a different area, ensuring that not a single moment of valuable mission time is lost. It can prioritize targets on the fly, choosing to extend its observation of a scientifically fascinating mineral vein while shortening a scan of a less interesting plane. As leading AI researcher Dr. Elena Torres puts it, these systems have evolved from simple tools into genuine partners. They don't just collect data, they interpret it, they predict future conditions, and they optimize their own performance to ensure the mission's success, acting as a remote extension of human curiosity and capability. This intelligence-driven approach is fundamentally rewriting the rules of exploration, transforming distant, unknown frontiers into familiar, mapped territories waiting for our arrival. These robotic emissaries are the fundamental infrastructure of this entire endeavor. Without their tireless, silent work, our maps would be blank. They are more than just cameras on a stick. They are incredibly sophisticated mobile laboratories, each one a marvel of engineering packed with a suite of specialized instruments designed to perceive the universe in ways we physically cannot. Think of them as having a form of synthetic synesthesia, where a single pass over a landscape doesn't just yield a picture, but a symphony of data. Their high-resolution cameras capture the visual landscape, but that's just the beginning. They carry spectrometers that break down sunlight reflected from a surface to reveal its chemical makeup, identifying minerals, ices, and organic compounds from hundreds of kilometers away. Magnetometers chart the invisible magnetic fields of planets, telling us about their molten cores and history. Radar instruments pierce through obscuring layers, like the thick clouds of Venus or the icy crust of Jupiter's moon Europa, to map the terrain hidden beneath. Each instrument adds a new layer of information, a new color to the palette these artists use to paint our picture of these distant worlds. The true test of their capability, however, isn't just in the data they collect, but in how they handle the immense challenges of deep space travel alone. The European Space Agency's Bepi-Colombo mission to Mercury is a perfect example of this high-stakes autonomy. Mercury's proximity to the Sun creates a terrifying environment of extreme radiation and gravitational pull. The communication delay means engineers on Earth can't joystick the spacecraft with any precision. So, Bepi-Colombo is equipped with an autonomous navigation system that constantly monitors its surroundings. If it detects that its trajectory is being affected by the Sun's overwhelming gravity or by slight variations in solar radiation pressure, it doesn't wait for a command from home. It makes a calculated decision in real time, firing its small thrusters for a fraction of a second to correct its course. This isn't a pre-programmed maneuver. It's an ongoing, intelligent conversation between the probe and its environment, a continuous process of sensing and reacting to ensure it stays on the precise path needed to eventually slip into orbit around one of the most difficult planets to reach. This level of self-reliance is what separates modern probes from their predecessors. They are not just passive collectors but active participants in their own missions. And these missions are marathons, not sprints. A probe like NASA Juno orbiting Jupiter is designed to operate for years in one of the solar system's most punishing radiation environments. It's not just surviving, it's constantly working, gathering terabytes of data on the gas giant's violent atmosphere, immense magnetic field, and mysterious interior structure. This longevity is a key multiplier of their value. A single probe can map an entire world's surface not just once, but repeatedly over many years, allowing scientists to track changes, to see new storms erupt on Mars, to monitor the shifting of ice on distant moons, to watch as a comet's surface evolves as it approaches the Sun. This temporal dimension turns a static map into a dynamic movie of a world, providing insights into its climate and geology that a single snapshot could never offer. The cumulative data from these long-duration missions is what builds the rich, deep, and ever-evolving cartographic databases that future explorers will rely upon. This incredible autonomy directly translates into a new era of accessibility and ambition for space exploration. Because these probes can largely take care of themselves, the cost and risk of missions are dramatically reduced. We don't need a massive, round-the-clock team of engineers on the ground for every single minute of a decade-long mission. This efficiency means space agencies and even private companies can launch more missions more often. Instead of one flagship mission to the outer solar system per generation, we can envision a steady stream of smaller, highly focused probes, one to map the methane lakes of Titan, another to dive through the plumes of Enceladus, another to orbit Uranus. This shift enables a strategy of distributed surveying, where a fleet of specialized robotic cartographers divvies up the work of mapping the solar system, each one contributing its unique piece to the grand puzzle. The next generation, already on drawing boards, will take this even further. They will be capable of making complex scientific decisions on their own, choosing which asteroids are most valuable to scan for mining, identifying the most promising sites for life on an icy moon, or even collaborating with other probes in a coordinated swarm to map a large area simultaneously. Their independence is the engine that is rapidly accelerating our journey from simply visiting other worlds to truly knowing them. While artificial intelligence provides the brain and autonomous probes act as the body, the true senses of these orbital cartographers come from a suite of remarkable technologies that allow them to perceive the universe in ways we can only dream of. Among these, one tool stands out for its breathtaking precision and versatility: LIDAR. The name itself, light detection and ranging, sounds almost simple, but its application is nothing short of magical. Imagine being able to fire millions of tiny, invisible laser pulses at a landscape from orbit, each one a photon-sized explorer. By meticulously measuring the exact nanosecond it takes for each pulse to travel down to the surface and bounce back to the sensor, a LIDAR system can calculate distances with an accuracy down to mere centimeters. This process, repeated in a blindingly fast torrent of light, allows the instrument to build a stunningly detailed three-dimensional point cloud of the terrain below. It's not a photograph, it's a perfect digital elevation model, a sculpture of data that captures every mountain, every valley, every boulder, and every crevasse in immaculate detail. This capability is revolutionary because it conquers two of the biggest obstacles in space exploration: darkness and obstruction. Optical cameras are useless on the night side of a planet or moon, and they can't see through the thick, acidic clouds of a world like Venus or the dusty haze of a global Martian storm. But LIDAR doesn't care about light or weather. It creates its own illumination, and its laser beams can penetrate thin atmospheres and even some surface materials to map what lies beneath. This was put to the test spectacularly during NASA's Mars 2020 mission, as the Perseverance rover descended towards the red planet in its dramatic 7 minutes of terror. Its landing system incorporated a specialized LIDAR called Lander Vision System, or LVS. In its final moments, the spacecraft switched from relying on pre-loaded maps to using this real-time LIDAR. It scanned the rapidly approaching ground, comparing the live 3D model to its onboard maps to identify the safest, flattest spot within its reach, automatically steering away from large rocks and craters that could have spelled disaster. It was a fully autonomous, split-second decision made by a robot using LIDAR, and it ensured a perfect touchdown in one of the most treacherous landing sites ever attempted. Yet for all its power, LIDAR only tells half the story. It gives us the shape of the world, but not its substance. This is where its perfect partners, multispectral and hyperspectral images, come into play. Think of it like this: if LIDAR is the cartographer's ruler and pencil, meticulously drawing the contours of the land, then spectrometers are their paint palette, revealing the vibrant colors of composition. These instruments don't just see in the red, green, and blue that our eyes perceive. They break down reflected light into hundreds of individual wavelengths, each one acting as a unique chemical fingerprint. A multispectral imager might have 10 or 15 of these specific channels, good for identifying broad categories of rock. But a hyperspectral imager is in another league entirely, capturing contiguous spectra across hundreds of bands. It can look at a patch of ground and not just say, "That's rock," but identify it specifically as olivine, or detect the subtle spectral signature of water molecules bound in minerals, or even differentiate between types of frost. This fusion of data is where the true cartographic magic happens. By layering the exquisite topographic detail from LIDAR over the rich compositional data from spectrometers, scientists can create a living, breathing map. They can see that a particular crater's steep northern wall is composed of iron-rich basalt, while its flat, sunny southern floor contains deposits of clay minerals that only form in the presence of water. This isn't just a map for navigation. It's a geological thesis and a resource prospector's guide, all in one. The evolution of these sensing technologies is a story of relentless miniaturization and increasing power. Early LIDAR systems were massive, power-hungry instruments that could only fly on the largest spacecraft. Today, thanks to advances in photonics and laser technology, we can build LIDAR units small enough and efficient enough to be mounted on tiny CubeSats or even small rovers. This democratization of sensing power means we can now envision constellations of small, inexpensive satellites working in concert, each equipped with these powerful eyes, to map an entire planet like Mars in high resolution in a matter of months instead of decades. The next frontier for these technologies is even more exciting. Researchers are developing quantum LIDAR systems that use entangled photons, which could provide even greater accuracy over longer distances while using less power. There's also work on more sophisticated spectral imagers that can detect the faint biosignatures of potential extraterrestrial life. These silent cartographers are not just getting smarter. Their very senses are becoming more acute, promising to reveal secrets of our solar system that are currently hidden in plain sight, waiting for the right tool to perceive them. This concept of distributed intelligence takes an even more radical and fascinating form with the emergence of swarm robotics, a field that draws its core inspiration not from supercomputers or massive satellites, but from the humble, ancient wisdom of nature. Look at a beehive or an ant colony. No single insect is in charge, barking out orders. There is no central command center. Instead, each individual operates on a simple set of local rules: follow the pheromone trail, help carry this food, protect the nest. And from this decentralized, almost mindless cooperation emerges a breathtakingly sophisticated and resilient system capable of building immense structures, finding food sources, and adapting to threats. Swarm robotics seeks to replicate this biological miracle on a technological scale, replacing a single, expensive, and vulnerable flagship robot with a vast constellation of small, simple, and cheap units. The promise is profound. Instead of sending one sophisticated cartographer to map a world, we could send 1,000. The advantages of this approach are transformative, especially when confronting the immense and varied landscapes of other worlds. First and foremost is resilience. In a traditional mission, a single critical failure, a crashed rover, a malfunctioning transmitter on an orbiter, can mean the catastrophic end of a multi-billion-dollar project that took decades to plan. A swarm operates on an entirely different principle. If one unit or even a dozen units fail by crashing into a cliff, being buried in dust, or simply wearing out, the mission doesn't end. The remaining members of the swarm automatically reconfigure, communicating with each other to cover the gaps left by their fallen comrades. The loss is a statistical footnote, not a mission-ending catastrophe. This allows us to take risks and explore environments we would never dare send a traditional, singular robot into: the unstable plumes of a geyser on a moon like Enceladus, the deep, shadowed ravines of a comet, or the treacherous, jagged terrain of a metal-rich asteroid. This resilience is paired with an unprecedented speed of coverage. A single rover like Curiosity or Perseverance on Mars is an incredible scientific instrument, but it moves at a glacial pace, covering perhaps a dozen miles over many years. It provides an exquisitely detailed look at one small postage stamp of the planet. A swarm of hundreds of small, hopping or rolling robots could blanket an area the size of a large city in a matter of days. They would spread out like a net, each member mapping its immediate vicinity with onboard cameras and sensors. Through constant communication, either directly with each other or through a relay orbiter, they would stitch their individual data points together into a seamless, high-resolution map. What would take a lone rover a decade to accomplish, a swarm could complete in a single season, providing a comprehensive survey of a vast region at a fraction of the time and cost. The true cutting edge of this technology lies in shapeshifting and adaptability. NASA's innovative shapeshifter concept is a stunning glimpse into this future. Imagine not a swarm of identical units, but a collective of specialized robots that can physically combine and separate like digital Legos. For a long journey, they might lock together into a sphere to roll efficiently across a smooth plain. When they encounter a steep cliff, the collective could break apart, with some units using propellers to fly up and over the obstacle while others might use grappling hooks to climb. Once at the top, they could reassemble into a different configuration, perhaps a long chain to lower a sensor into a deep fissure. This isn't a single tool. It's an entire toolbox that can dynamically reshape itself on the fly to meet any challenge the environment presents. It's the ultimate expression of adaptability, a robotic swarm that is as versatile and resilient as the natural systems that inspired it. As this technology matures, its applications will become the bedrock of future exploration. The first truly comprehensive maps of asteroids won't be made by a single orbiting satellite, but by a cloud of small probes descending upon it, mapping its every nook and cranny from every angle simultaneously to create a perfect 3D model. Preparing for a human mission to Mars could involve deploying swarms of small, solar-powered mapping rovers to every potential landing site in a vast region, providing ground truth data that orbital images can't match. They could spend months characterizing the soil mechanics, the dust properties, and the local resource availability, creating a perfect digital twin of the site long before the first human crew ever leaves Earth. This shifts our paradigm from speculative exploration to informed settlement, turning the silent, unknown void into a well-charted and prepared new frontier, all thanks to the collective power of thousands of tiny, silent cartographers working in perfect, decentralized harmony. But the raw streams of data from these individual sensors, the breathtaking LIDAR scans, the intricate spectral fingerprints, the subtle gravitational tugs, are like isolated pieces of a grand, cosmic puzzle. They are individually fascinating, but their true, transformative power is only unlocked when they are masterfully combined. This process, known as data fusion, is the intellectual engine room of modern orbital cartography. It's where the scattered whispers of different instruments are woven together into a single, coherent, and shouting narrative of a world. Each type of sensor speaks a different language. A thermal imager reads heat, a gravimeter reads density, a spectrometer reads chemistry. The monumental task of advanced algorithms is to act as a universal translator, taking these disparate dialects and integrating them into a unified story that is far greater than the sum of its parts. This fusion is far more complex than simply overlaying one image on top of another. It's a sophisticated process of reconciliation and enhancement. Often, data from different sources can appear to conflict. A radar scan might suggest a certain surface roughness that doesn't perfectly align with the topography suggested by a laser altimeter, or a gravitational anomaly indicating a dense subsurface mass might not have an obvious surface feature visible in optical images. The algorithms are designed to be detectives, not clerks. They don't just paste the data together, they investigate these discrepancies, using probabilistic models and deep learning to determine the most likely true state of the environment. They intelligently fill in the gaps where one sensor might have blind spots, using a high-resolution camera to sharpen a lower-resolution thermal map, or using a known mineral spectral signature to interpret a patch of terrain that was in shadow during a LIDAR pass. The output is a seamless, multi-layered digital twin of the landscape, a holistic map that tells you not just where a mountain is, but what it's made of, how stable its slopes are, and what might be buried beneath it. The practical value of this synthesized intelligence is immense, particularly when it comes to the economics of space. Consider the critical challenge of in situ resource utilization, the idea of living off the land by extracting water, minerals, and building materials from other worlds. A prospector doesn't just need a map that shows a flat plain. They need a map that screams, "Dig here." This is where fusion pays its way. By fusing LIDAR topography that identifies a smooth, accessible area with hyperspectral data that reveals a strong water signature in that exact same spot, the map can confidently highlight a prime candidate for a future water extraction operation. It can cross-reference that with thermal data showing the ground has stable temperatures, and even gravitational data suggesting no large subsurface cavities that could cause a collapse. This isn't a map for exploration anymore, it's a prospectus for development. It transforms a gamble into a calculated investment, providing the actionable intelligence needed to justify the immense cost of setting up industrial operations millions of miles from Earth. Beyond commerce, this integrated approach is the bedrock of serious scientific discovery and strategic infrastructure planning. A geologist studying Mars isn't just looking at a picture of a canyon. They are using a fused map that layers visual context, mineral composition, stratigraphic layers from subsurface radar, and erosion patterns from wind models. This allows them to reconstruct the planet's hydrological history with a clarity that was previously impossible. For an engineer planning a permanent lunar base, the map they consult is a multi-layered decision support system. It will have layers they can toggle on and off. One layer for solar illumination levels to optimize power collection, another for communication line of sight with Earth, another for regolith composition to find the best building materials, and another for proximity to scientific points of interest. This seamless blending of environmental, geological, and logistical data is what turns a barren, alien landscape into a manageable, understandable place ready for human habitation and operation. It is the ultimate act of preparation, converting the unknown into the known and the dangerous into the manageable, all through the silent, digital alchemy of data fusion. Yet for all their sophisticated intelligence and collaborative power, these silent cartographers face a working environment of almost unimaginable hostility. The blank spaces they are tasked with filling in on our celestial maps aren't just unknown, they are actively trying to destroy the very tools we use to know them. Every alien world presents its own unique gauntlet of extreme conditions, a series of brutal tests that push engineering and software to their absolute limits. The vacuum of space itself is a relentless foe, offering no air to cool sensitive electronics and allowing charged particles from the sun to build up static electricity that can arc across circuit boards, frying them instantly. On airless bodies like our moon or an asteroid, the temperature swing between direct sunlight and shadow is not a gentle gradient but a violent cliff face. One moment a component can be baking at well over 100 degrees Celsius, and minutes later, as it rotates into darkness, it's plunged into deep freeze at nearly 200 degrees below zero. This thermal shock, repeated over thousands of cycles, can crack metal, delaminate composites, and shatter solder joints, demanding materials and designs that are not just strong, but incredibly flexible and resilient. Perhaps no place in our solar system exemplifies this challenge more starkly than the surface of Venus. It is a vision of hell made real, a crushing, corrosive, and infernal environment that has defeated every probe humanity has ever landed there in a matter of hours. The pressure at the surface is 92 times that of Earth, equivalent to being nearly a kilometer underwater. The atmosphere is a suffocating soup of carbon dioxide with clouds of sulfuric acid, capable of eating through most metals and ceramics. And the temperature is a constant 462 degrees Celsius, hot enough to melt lead, zinc, and even some types of stainless steel. To map this world, you cannot simply point a camera from orbit. Its impenetrable cloud deck obscures the surface from view, requiring radar and other penetrating instruments. And to send a lander that could survive more than a few fleeting moments requires a radical rethinking of almost every component. Engineers are developing electronics using silicon carbide that can continue to function at these extreme temperatures, and designing pressure vessels not from aluminum, but from titanium and exotic superalloys. They are even experimenting with entirely mechanical computers, using gears and levers instead of silicon chips, to create a rover that could theoretically operate for months on the surface, slowly mapping a landscape that liquefies our standard tools of exploration. But the challenges aren't only physical. they are also a matter of time and distance, creating a profound cognitive gap between the robot and its creator. The vastness of space introduces a communication delay that makes real-time remote control a complete impossibility. When the Perseverance rover is on Mars, its signals take anywhere from 5 to 20 minutes to travel one way, depending on the planet's positions in their orbits. This means that by the time an engineer in California sees that the rover's wheels are slipping on a dangerous slope, the vehicle could have already been stuck or damaged for the past 20 minutes. For missions to the outer solar system, this delay stretches into hours. At Jupiter, the round-trip communication time is over an hour and a half. At Saturn, it's more than 2.5 hours. This forces a fundamental shift in the very philosophy of mission design. These robotic cartographers cannot be puppets on a string from Earth. They must be fully autonomous agents, endowed with enough onboard intelligence to perceive danger, diagnose problems, and execute life-saving maneuvers entirely on their own. To conquer these multifaceted threats, engineers employ a threefold strategy of redundancy, adaptability, and exhaustive simulation. Critical systems on every probe and rover are duplicated or even triplicated. If one main computer fails, a pristine backup instantly wakes up and takes the reins. This redundancy extends to sensors, thrusters, and power systems, creating a machine that can suffer multiple failures and still complete its core mission. But redundancy is a blunt instrument. The true elegance lies in adaptive software. This is AI that doesn't just follow a map, but can literally rewrite its own priorities based on the health of the spacecraft. It can notice that a particular wheel motor is drawing more power than usual and decide to avoid steep inclines for the rest of the mission. It can detect a memory chip starting to fail and seamlessly shift all its functions to a backup bank while isolating the damaged component. This is not pre-scripted behavior. It is genuine machine self-preservation, a form of digital instinct programmed to ensure survival at all costs. This level of reliability is forged not in space, but in brutal testing facilities on Earth. Before a mission ever gets near a launch pad, its components are subjected to a campaign of simulated torture that mirrors the horrors they will face. They are baked in ovens, frozen in liquid nitrogen chambers, blasted with deafening sound vibrations that mimic the violence of a rocket launch, and bombarded with radiation in particle accelerators. Entire Martian landscapes are recreated in giant sandboxes to test rover mobility, while special chambers simulate the alien atmospheres of Titan or Venus. Each solved challenge, each component that survives the torture test, does more than just ensure the success of a single mission. It pushes the entire field of robotics and materials science forward, creating spin-off technologies that benefit medicine, aviation, and manufacturing here on Earth. The relentless, brutal demands of mapping our solar system are, in fact, one of the most powerful engines for innovation we have, forcing us to build machines that are smarter, tougher, and more capable than we ever dreamed possible. This growing reliance on autonomous intelligence forces us to confront a series of profound and deeply human questions. Who is ultimately responsible for the decisions made by a machine operating millions of miles away? If an AI-driven probe, upon discovering a previously unknown cave system brimming with scientific potential, decides on its own to divert all power from its primary mission to explore it, has it acted correctly? What if that diversion means it fails to map a critical area needed for a future human landing? The chain of accountability becomes blurred when the decision-maker is not a person in a mission control center, but a complex algorithm interpreting its pre-programmed goals. This isn't a distant philosophical puzzle. It's a practical design challenge that engineers and ethicists are grappling with today. The potential for unintended consequences is vast. A prospecting rover tasked with finding water ice might determine the most efficient way to do so is to use a small charge to create an explosion and analyze the debris plume. But what if that same site is considered a sacred archaeological record of the solar system's history by scientists? The machine's concept of mission success is purely functional, devoid of the cultural, historical, and ethical context that humans would naturally apply. To navigate this new terrain, leading voices in the field like Dr. Liam Chen are championing the development of robust ethical AI frameworks. The goal is to move beyond simply programming a probe with a set of commands and instead embed a deeper layer of human values into its core decision-making processes. This isn't about creating a robot philosopher. It's about building a system of weighted priorities and constraints that mirror our collective judgment. Imagine an algorithm that doesn't just have a primary goal, like map mineral deposits, but also has a set of inviolable rules, like never approach within 1 kilometer of a site designated as a potential region of biological interest, or always prioritize the preservation of the original geological context over expedient data collection. These frameworks act as a digital conscience, a set of guardrails that ensure the autonomous agent's pursuit of its objectives remains aligned with our broader, more nuanced exploration goals. It's the difference between a tool that simply does what you told it to do and a partner that understands the spirit of why you gave it that task. Central to making this partnership work is an uncompromising commitment to transparency. The algorithms that guide these robotic cartographers cannot be black boxes where decisions are made inscrutably. For scientists on Earth to trust the data and the choices made by the machine, they must be able to audit its logic. This means developing AI systems that don't just arrive at a conclusion but can also provide a clear, traceable rationale for their actions, a sort of decision log that explains, I chose to navigate to location X because it offered a 95% probability of fulfilling the primary objective while adhering to all safety and preservation constraints, and I rejected location Y due to 15% risk of damaging a scientifically sensitive area. This level of transparency is what builds trust and ensures accountability. It allows human overseers to understand the machine's behavior, learn from its choices, and continuously refine the ethical frameworks that guide it. This iterative process of action, explanation, and refinement is how we create a true collaboration between human intuition and machine execution. These ethical considerations are already actively shaping the design and deployment of every new mission. The software running on the latest generation of Martian rovers includes increasingly sophisticated fault protection and decision-making protocols that weigh scientific value against potential preservation concerns. Mission planners are now including ethicists on their teams, people who help draft the rules of engagement for these robotic explorers long before they leave the launch pad. This careful, deliberate balancing act between the drive for innovation and the necessity of caution is what will define the responsible exploration of our solar system. We are learning to send our ambition ahead of us not as a blunt instrument, but as a thoughtful, considerate extension of our will, one that prepares the way not just for our feet, but for our values. And it is on our own moon, that familiar silvery companion in the night sky, where these principles of robotic cartography have been perfected into a breathtakingly precise science. The moon serves as the ultimate celestial testbed, a harsh but accessible environment where every technology, from autonomous navigation to high-resolution sensing, can be proven just a short hop from Earth before we send it on a years-long journey to the outer solar system. For over a decade, one robotic sentinel has been the undisputed master of this domain, NASA's Lunar Reconnaissance Orbiter, or LRO. Since its arrival in lunar orbit in 2009, this single spacecraft has fundamentally rewritten our understanding of Earth's companion. Its suite of 7 powerful instruments has been engaged in a relentless, silent campaign of measurement, firing its laser altimeter over 6 billion times to map the topography of the entire Moon with meter-scale accuracy. But its most critical work has been in the search for one of the most precious resources in the solar system, water ice, locked away in the perpetual, frigid shadows of polar craters where temperatures hover near absolute zero. This water isn't just for drinking, it's the key to a sustainable future in space. It can be split into hydrogen and oxygen for rocket fuel, effectively turning the Moon into a cosmic gas station. LRO's instruments, like the Lunar Orbiter Laser Altimeter and the Lyman Alpha Mapping Project, have peered into these inky black abysses, not with light, but with lasers and the faint glow of starlight reflected off hydrogen, to definitively confirm the presence of this frozen treasure. It has created detailed maps of these shadowed regions, identifying specific craters where the concentration is highest and the terrain is most accessible. This isn't speculative science, it's a practical prospector's guide, a definitive atlas pointing to where humanity should establish its first off-world foothold to leverage these local resources. This incredible dataset has become the foundational layer for a new wave of exploration, one driven not just by governments but by commercial ambition. Companies like SpaceX, Intuitive Machines, and Robotic are not starting from scratch. They are building their business plans directly on the cartographic bedrock provided by LRO and other missions. When SpaceX plans its Starship lunar landings, it will use these high-resolution maps to select the optimal spot, a flat area with ample sunlight for solar power, situated just a short distance from a shadowed crater brimming with water ice. They can analyze the regolith's bearing strength to ensure their massive spacecraft won't sink into the dust and plot out routes for rovers to travel from the landing pad to the resource extraction site. The maps allow them to de-risk their missions to an incredible degree, transforming a gamble into a calculated engineering project. This seamless handoff from a government science mission to commercial utility is a powerful model for the future, where robotic cartographers act as the advance team for an entire economic ecosystem. Perhaps the most revolutionary aspect of this lunar mapping effort is that it is not a static snapshot. We are not looking at a single, frozen map drawn in 2010. This is a living document of the Moon, a dynamic dataset that is constantly being updated and refined. The lunar surface is a surprisingly active place, constantly reshaped by a rain of micrometeorites. LRO's cameras have captured the before and after images of hundreds of these fresh impacts, some carving out craters over 10 meters wide. The orbiter also meticulously tracks the changing patterns of light and shadow as the sun's angle shifts over the long lunar day, information critical for planning permanent solar power installations. Every new mission that arrives, whether an orbiter from India or a lander from a private company, contributes its own data points, which are fed back into the master lunar model, making it sharper, more accurate, and more current with every passing month. This creates an ever-evolving digital twin of the Moon that is arguably more detailed in some aspects than our maps of the ocean floor here on Earth. The profound success of this multi-year lunar mapping campaign provides an invaluable blueprint for how we will approach every other celestial body. The lessons learned from operating LRO, how to process its immense data streams, how to automate its navigation, how to use its instruments in concert have been directly applied to missions at Mars and beyond. The Moon has shown us that comprehensive precursor mapping is not a luxury. It is an absolute necessity that de-risks every subsequent mission, both robotic and human. It allows us to replace fear of the unknown with confidence born from data. The detailed maps of the Apollo landing sites, showing the discarded descent stages and even the footpaths of the astronauts, stand as a powerful testament to this capability. They prove that we can create a cartographic record so precise that we can navigate from orbit not just to a general region, but to a specific human-scale artifact left behind 50 years ago. This is the powerful legacy of the silent cartographers at the Moon. They have turned our nearest celestial neighbor from a distant world into a familiar landscape, ready and waiting for our return. While the Moon serves as our nearby proving ground, Mars stands as the ultimate prize, a world that has captivated our collective imagination for centuries and has become the most intensely mapped planet in our solar system, aside from Earth. This relentless cartographic campaign is a grand international collaboration, a symphony of orbital observers each playing a different instrument. For over 2 decades, a fleet of orbiters from NASA, the European Space Agency, and others have encircled the red planet, transforming it from a distant, blurry red disk into a world we know in intimate, spectacular detail. Missions like Mars Express with its penetrating radar and MAVEN, which studies the thin Martian atmosphere, aren't just taking pictures, they are each conducting a deep, specialized examination. Mars Reconnaissance Orbiter, perhaps the workhorse of the fleet, has been so prolific that its high-resolution camera, HIRISE, has imaged nearly the entire planet in stunning clarity, allowing scientists to see features as small as a dinner table from hundreds of kilometers away. This isn't just mapping, it's a continuous planetary-scale health checkup, monitoring dust storms, tracking seasonal changes in polar ice caps, and watching for fresh landslide scars on crater walls. The true power of this multi-generational effort is revealed in the breathtaking precision of modern Martian landings. The journey of the Perseverance rover to the surface of Mars in 2021 was a masterpiece of engineering, but it was a masterpiece painted on a canvas prepared by decades of orbital cartography. Mission planners didn't just pick the Jezero crater landing site because it looked interesting. They selected it because orbital spectrometers had identified specific clay minerals there that form exclusively in the presence of water, and because topographic maps created from laser altimetry proved that the crater once held a vast lake with a clearly visible river delta fossilized on its floor. The orbiter's data allowed engineers to model the wind patterns and atmospheric density over the landing site for that particular Martian season, fine-tuning the rover's landing system for a pinpoint touchdown. As the rover descended, its onboard computers compared real-time LIDAR images of the approaching ground to these pre-loaded orbital maps, autonomously steering away from boulder fields and sand traps that had been identified as hazards from orbit. This seamless handoff from orbital scout to ground-based explorer is the culmination of the silent cartographer's work, turning a deadly descent into a precisely choreographed ballet. Beyond guiding robots, this ever-growing library of maps is quietly laying the groundwork for human arrival. The most critical question for any sustained human presence is the availability of water, not just for drinking but for making oxygen to breathe and hydrogen for rocket fuel. Here, orbital cartography has provided the answer. The Mars Odyssey orbiter, using a neutron spectrometer, first detected the telltale signature of vast amounts of hydrogen just beneath the surface in the mid-latitudes, strongly suggesting the presence of water ice. Later, the ground-penetrating radar on Mars Reconnaissance Orbiter was able to confirm this, mapping entire glaciers of pure water ice buried under just a meter or two of protective dust. These are not mere hints. They are mapped deposits, literal treasure maps showing future colonists where to dig. Planners can now overlay these water resource maps with maps of solar energy availability, geological stability, and potential radiation exposure to select the optimal sites for the first Martian bases, ensuring they are situated near the necessary resources for long-term survival and independence from Earth. This process of understanding is beautifully cumulative, a constant state of building upon what came before. Each new orbiter carries more advanced instruments than the last, but its mission is informed by the questions raised by its predecessors. The discovery of seasonal methane gas plumes by one spacecraft leads to the design of a subsequent mission with more sensitive spectrometers to pinpoint the source. A rover's ground-level analysis of a rock layer provides a truth point that allows scientists to calibrate the orbital spectral data, which then can be used to accurately identify that same rock type across the entire planet. It's a virtuous cycle of discovery where orbiters guide rovers to the most interesting spots, and the rovers, in turn, send back data that makes the orbital maps smarter and more insightful. This collaborative dance between orbit and surface is creating a living, breathing understanding of Mars, its ancient, water-rich past, its transition to a cold desert, and its potential, however faint, for harboring signs of past life. The silent cartographers above have not just drawn a map of Mars, they have written its first multi-volume biography, and we are still eagerly turning the pages. While the planets and moons present their own set of challenges, they are at least familiar in their general structure, roughly spherical, with enough gravity to provide a predictable up and down. But to truly grasp the outer limits of our cartographic ambitions, we must turn our attention to the solar system's nomads, the asteroids and comets. These small, often misshapen bodies are the ultimate test of autonomous mapping, a chaotic and unpredictable environment where the very rules of physics seem to play by a different book. Their irregular shapes, some looking like spinning tops, others like jagged diamonds or even canine bones, create gravitational fields that are lumpy and uneven, pulling a spacecraft in unexpected directions. Their gravity is so faint that a probe couldn't land in the traditional sense. It would have to gently rendezvous and perhaps even grapple onto the surface, all while the body beneath it might be rotating rapidly, completing a full turn every few hours and hurling loose material into the void. Mapping this environment isn't just a technical challenge. It's a high-stakes ballet where the dance floor itself is moving, crumbling, and shifting with every step. The OSIRIS-REx mission to asteroid Bennu stands as a breathtaking testament to what is possible. When the spacecraft first arrived, scientists were stunned. Their initial models, based on Earth-based radar, had suggested a relatively smooth, sandy surface. Instead, OSIRIS-REx found a world of pure chaos, a jagged rubble pile strewn with car-sized boulders, with a surface so porous and loose it was likened to a plastic ball pit. In this environment, a pre-programmed landing sequence would have been catastrophic. The spacecraft's entire mission hinged on its autonomous mapping systems. It spent months circling Bennu, using its laser altimeter and suite of cameras to build a digital model of the asteroid so precise it could identify a single pebble. This map wasn't just for show, it was the essential tool for the mission's climax, the touch-and-go sample collection maneuver. The onboard navigation system compared its real-time camera images to this ultra-high-resolution map, autonomously steering itself toward a safe patch of ground no larger than a few parking spaces, avoiding countless hazards in real time to briefly kiss the surface and retrieve a precious sample. This was silent cartography in its most advanced form, a robot using a map it created itself to perform a delicate and unprecedented maneuver over 200 million miles from any human help. The precision of these maps unlocks a future that sounds like science fiction but is rapidly approaching reality. Asteroid mining. These seemingly barren rocks are actually treasure chests floating in the void. Some, known as C-type asteroids, are rich in water ice and carbon-based compounds, which can be broken down into life-supporting water and breathable air for astronauts, as well as hydrogen and oxygen for rocket fuel. Others, the M-type asteroids, are literally mountains of metal, iron, nickel, cobalt, and precious metals like platinum and gold, formed from the core of a long-dead protoplanet. A detailed map is the first prospectus for this new economy. It allows a mining company to evaluate a candidate asteroid not as a blurry dot, but as a specific asset. The map reveals the topography for landing equipment, identifies the distribution of valuable materials via spectral analysis, and assesses the structural integrity of the body itself to plan safe excavation. This transforms a high-risk gamble into a calculated investment, turning these distant curiosities into actionable, accessible resources that could one day fuel the entire infrastructure of space exploration, allowing us to build and refuel in space without the colossal cost of launching everything from the bottom of Earth's gravity well. Yet the value of this meticulous mapping extends far beyond commerce and into the realm of planetary security. The same technologies that allow a probe to gently touch an asteroid also allow us to precisely track those that might pose a threat to Earth. The gravitational pull of planets can subtly alter the orbits of near-Earth objects over time, and a tiny uncertainty in their position today can translate into a massive uncertainty in their future path. By sending a mapping mission to a potentially hazardous asteroid, we can measure its exact mass, density, and shape, creating a perfect digital model. This model allows astronomers to calculate its trajectory with phenomenal accuracy, predicting its movement centuries into the future and definitively ruling out or confirming a potential impact. But it goes even further. This detailed knowledge is the key to deflection. If we ever did find an asteroid on a collision course, knowing its precise composition and structure would be critical. Is it a solid chunk of metal or a loose pile of rubble held together by feeble gravity? The method we would use to nudge it off course, a gravitational tractor, a kinetic impactor, or a nuclear device, depends entirely on the data contained within its map. In this light, the silent cartographers are not just pathfinders and prospectors. They are also sentinels, their work providing the essential intelligence needed to protect our planet. Ultimately, the successful mapping of these small, elusive targets represents a fundamental expansion of human capability. It proves that there is no world, no matter how small, weird, or distant, that our robotic emissaries cannot reach, understand, and chart. Each asteroid and comet mapped is another foothold, another resource depot, another piece of the solar system puzzle falling into place. They are no longer just points of light or subjects of scientific curiosity. Through the painstaking work of orbital cartography, they become waypoints on a future map of human activity, dots to be connected in the sprawling network of interplanetary commerce and exploration. This is how the solar system truly opens up to us, not with a single giant leap, but with a billion tiny, precise measurements, each one quietly adding another detail to the master atlas these silent cartographers are compiling for our future. But the ambitions of these silent cartographers extend far beyond the familiar worlds of our own solar system. Their ultimate destiny lies in the unimaginable vastness between the stars. This is the realm of interstellar cartography, a field that moves from the challenging to the truly visionary, aiming to map planets orbiting other suns. The distances involved are so colossal that they defy human intuition. The very closest star to our own, Proxima Centauri, is about 4.2 light-years away. To put that in perspective, if the distance from the Earth to the Sun were shrunk down to the size of a single page in a book, the distance to Proxima Centauri would still be over 4.5 miles. Sending a conventional, chemically powered probe on such a journey would take tens of thousands of years, arriving long after our civilization has been forgotten. To cross this gulf within a human lifetime requires a leap of technology so radical it borders on science fiction, and that is precisely what initiatives like Breakthrough Starshot are attempting to achieve. The core concept is as breathtaking as it is simple. Instead of one large, heavy spacecraft, the idea is to launch a fleet of thousands of tiny probes, each weighing little more than a gram and attached to a light sail no bigger than a postage stamp. From a facility on Earth, an enormous array of powerful ground-based lasers would focus a beam of light onto these sails, accelerating them to 20% the speed of light within mere minutes. Imagine these tiny craft, these star chips, being pushed by a beam of pure energy, racing out of the solar system faster than any human-made object in history. After a 20-year journey, this swarm would hurtle past the Proxima Centauri system not as a visiting ship, but as a high-speed reconnaissance flyby. Their task would be to conduct a full survey in a blindingly fast flash as they pass by, collecting every possible byte of data before continuing on into the endless void, becoming the first silent whispers of humanity in the interstellar medium. The level of autonomy required for such a mission is almost incomprehensible. With a one-way communication delay of over 4 years, there is absolutely no possibility of remote control. By the time an engineer on Earth even saw the data that a problem was occurring, the probes would have been dead for years. These star chips would have to be the most intelligent, self-reliant robotic cartographers ever conceived. Their onboard AI would need to make millions of critical decisions in a fraction of a second. As the swarm approaches the target, it would have to autonomously coordinate its members, deciding which probes should focus on which planets, how to avoid any potential debris rings, and how to optimally angle their miniature cameras and sensors. They would have to diagnose their own health, compensate for any damage sustained during the decades-long journey through interstellar space, and prioritize which datasets are most critical to transmit back to Earth, all while traveling at over 134 million miles per hour. This isn't just programming, it's the creation of a digital consciousness designed for a single, ultimate purpose: to see what lies around another star and to tell us the story. The payoff for succeeding in this monumental endeavor would be nothing less than a revolution in our understanding of the universe. The data packets that finally trickle back to Earth years after the flyby would contain the first ever detailed maps of an exoplanet. We wouldn't just know that Proxima Centauri b is there, we would see it. We could map its continents and oceans if it has any. We could analyze its atmosphere for the chemical signatures of life, the telltale combinations of oxygen, methane, and other gases that scream biology. A single, grainy image of a light blue dot with white clouds and green landmasses would fundamentally shatter our cosmic isolation, forever altering humanity's place in the cosmos. It would tell us that we are not alone, or if we are, that the potential for life is woven into the fabric of the galaxy. These maps would become the ultimate motivation, the irresistible lure that finally pushes us to become an interstellar species. They would transform these distant points of light from abstract astronomical curiosities into real places, with names and geographies and futures that we might one day be a part of. This visionary endeavor represents the absolute pinnacle of the silent cartographer's art. It is the ultimate expression of sending our eyes and our intelligence ahead of our physical presence. Every lesson learned from mapping the moon, navigating the ruble piles of asteroids, and operating rovers on Mars with 20-minute delays is a foundational step toward making interstellar cartography possible. It demands a perfect fusion of laser physics, materials science, miniaturization, and artificial intelligence, pushing every single discipline to its breaking point and beyond. The challenges are immense, perhaps even insurmountable with our current understanding, but the mere attempt forces innovation on a scale rarely seen. Whether the first maps of another star system arrive in 50 years or 500, the very act of working toward this goal expands the boundaries of what we believe is possible, ensuring that the silent, meticulous work of mapping the unknown continues long after our own solar system has been fully charted and has become just another familiar neighborhood in our galactic backyard. Yet for all their staggering speed and precision, these autonomous systems would be little more than sophisticated data vacuums without the guiding hand of human curiosity. The true magic happens not in the cold, silent vacuum of space, but back here on Earth, in the labs and offices where scientists pore over the torrent of information these robotic scouts send home. This is where the collaboration between human and machine reaches its zenith, a beautiful synergy that leverages the unique strengths of both. The machines provide the sheer, unassailable scale and precision. They are the ultimate fact gatherers, tirelessly measuring, cataloging, and transmitting with a patience and endurance no human team could ever match. But it is the human mind that provides the context, the creativity, and the why. A machine can identify a specific mineral signature on a Martian cliff face, but it takes a geologist to look at that data, weave it together with other clues, and spin a compelling story about an ancient river delta that once flowed there billions of years ago. The AI offers the what and the where, but the human scientist asks the how and the why, turning a sterile day to point into a profound insight about the history of our solar system. This partnership is a continuous, iterative dance of discovery. It often begins with a human-defined question. A planetary scientist, for instance, might have a hypothesis about volcanic activity on a distant moon. They then task the orbital cartographers, the satellites, and their AI brains with gathering specific data to test that idea. The machines go to work, scanning vast areas to map lava flow boundaries, measuring thermal emissions, and analyzing surface composition. They process this data and present it back to the scientists not as raw numbers, but as a synthesized map highlighting areas of interest. Now the human intuition takes over again. The scientist studies the map, sees an unexpected pattern, perhaps a series of fissures that don't align with current models, and formulates a new, more nuanced question. This leads to a new command being sent to the orbiter. Focus on this area, use your higher resolution spectrometer, look for these specific compounds. This feedback loop of human curiosity and machine execution is what accelerates our understanding at an exponential pace, with each partner making the other smarter and more effective. As the technology evolves, the interfaces for this collaboration are becoming breathtakingly immersive, moving far beyond flat screens and spreadsheets. Researchers are now using virtual and augmented reality systems to literally step inside the maps their robotic partners have created. Imagine a geologist standing in a lab on Earth, but wearing a VR headset that transports them to the surface of Mars. They are surrounded by a full-scale, three-dimensional rendering of the Jezero crater delta, built from billions of data points collected by the Mars Reconnaissance orbiter and the Perseverance rover. They can walk around a rock outcrop, crouch down to examine the stratigraphy in a cliff face, and even use a virtual tool to take a spectral reading, all without ever leaving Earth. This level of immersion allows for intuitive discovery, letting scientists spot patterns and relationships that might be missed when looking at a two-dimensional map. It is the ultimate fusion of human spatial reasoning and machine-generated data, collapsing the millions of miles of empty space into a shared workspace where human and machine can truly explore together. This deeply integrated partnership is reshaping the very nature of scientific exploration, ensuring that our journey into the cosmos is driven not just by cold efficiency, but by our innate sense of wonder. The machines handle the dangerous, the tedious, and the impossibly complex calculations, acting as our robotic proxies and tireless assistants. This frees the human experts to do what they do best: dream, hypothesize, and synthesize. They can focus on the big picture, drawing connections between disparate discoveries to build grand, unifying theories about planetary formation and evolution. The robotic cartographers provide the notes, but the human scientists compose the symphony. This ensures that our expansion into the solar system remains a deeply human endeavor, one that satisfies our practical needs for resources and safety, while also feeding our timeless desire to simply understand the universe around us and our place within it. This transformation of unknown frontiers into charted territories is what finally unlocks the true economic potential of space, moving it from the realm of government-funded exploration into the domain of viable commerce. Think of these detailed celestial maps not as simple pictures, but as the very first and most critical piece of infrastructure for a new economy, the cosmic equivalent of the first accurate nautical charts that opened up the age of sail and global trade. Without them, every venture into space is a blind, high-risk gamble. With them, it becomes a calculated investment. A mining company, for instance, isn't just guessing that a certain asteroid might contain valuable metals. They are consulting a prospectus generated by silent cartographers. These maps, built from spectral analysis and LIDAR topography, can quantify the likely concentration of platinum, gold, or rare earth elements within a specific space rock, allowing the company to secure funding based on hard data rather than hopeful speculation. This shifts the business model from high-risk exploration to lower-risk extraction, fundamentally changing the financial calculus of asteroid mining. The same principle applies to the nascent field of space tourism. For a company planning to offer lunar flybys or expeditions to a future orbital hotel, safety and the customer experience are paramount. The thrill of seeing the far side of the moon is dramatically enhanced when the flight path is plotted using ultra-high-resolution maps that ensure a smooth ride and maximize spectacular views of landmarks like the Shackleton crater. On a more practical level, these maps are indispensable for infrastructure development. The engineers designing the first permanent lunar base aren't working from sketches. They are using integrated 3D models that layer ground stability data from radar, solar exposure patterns for energy planning, and precise topography for laying out landing pads, habitats, and connecting roadways. This allows for prefabrication and precise planning on Earth, reducing costly and dangerous on-site construction work, and ensuring that every module and vehicle is designed for the specific, mapped realities of its destination. This de-risking effect is the single most powerful catalyst for attracting private capital. Investors, by their nature, are drawn to environments where the variables are understood and quantified. The meticulous work of the silent cartographers provides that certainty, transforming the perceived vacuum of space into a landscape of defined opportunities. A venture capitalist can now look at a business plan for a Martian water extraction operation and see not just a visionary idea, but a proposal backed by orbital data pinpointing the exact location of subsurface ice deposits, their estimated purity, and the surrounding terrain's suitability for heavy machinery. This confidence opens the floodgates of private funding, which in turn accelerates the pace of development far beyond what any single government program could achieve. We are already seeing this virtuous cycle in action. The precise lunar maps provided by missions like the Lunar Reconnaissance Orbiter didn't just aid NASA. They directly enabled companies like Robotic and Intuitive Machines to plan their commercial lander missions because they knew exactly where they were going and what to expect upon arrival. This creates a powerful, self-reinforcing feedback loop that benefits everyone, especially the mappers themselves. As new commercial missions launch, whether they are miners, tourism operators, or construction firms, they become new sources of incredibly valuable data. A commercial lander will often carry its own suite of sensors, capturing ground-level images and measurements that can be fed back to improve the orbital maps. This constant stream of new information from a growing number of actors means the maps become living documents, continuously updated and refined. The demand from industry for even higher resolution, more specialized maps then drives further investment into the next generation of mapping satellites and probes, equipped with even more advanced sensors. The economic activity enabled by the maps directly funds the technology that makes the next set of maps even better. In this way, the silent cartographers do not just enable the space economy. They are a thriving and essential industry within it, their own work becoming both a public good and a valuable commercial commodity, charting the course for humanity's economic expansion into the final frontier. Perhaps the most profound impact of these meticulously crafted maps lies not in a laboratory or a boardroom, but in a sixth-grade classroom, where a student puts on a virtual reality headset and gasps as they find themselves standing on the dusty, rock-strewn surface of Mars. This is the transformative power of educational and public outreach, where the raw data of orbital cartography is woven into immersive experiences that ignite curiosity and shape young minds. The maps created by these silent machines are far more than scientific tools. They are bridges of understanding, connecting the complex work of engineers and scientists to the innate sense of wonder within every person. By translating terabytes of spectral data and laser point measurements into interactive, visually stunning models, space agencies perform a crucial act of translation, turning esoteric information into a universal language of exploration that anyone can understand and be inspired by. Platforms like NASA, Eyes on the Solar System, are the gateways to this new frontier of learning. This isn't a static website with a few pictures. It's a sophisticated, real-time simulation built directly from the data streams of actual missions. A user can choose any date, past or future, and see the exact positions of every planet, moon, and spacecraft in the solar system at that moment. They can hitch a virtual ride on the Juno spacecraft as it screams over Jupiter's cloud tops, or follow the Perseverance rover along its actual traverse through Jezero crater, seeing the landscape unfold exactly as the rover's cameras did. This level of interactivity demystifies the scale and dynamics of our cosmic neighborhood in a way a textbook diagram simply cannot, providing an intuitive, kinesthetic understanding of orbital mechanics, planetary geology, and the sheer audacity of interplanetary travel. It makes the student not just a passive observer, but an active participant in the ongoing story of exploration. The educational value of these resources in promoting STEM, science, technology, engineering, and mathematics cannot be overstated. For a teacher, these interactive maps are a goldmine of engaging curriculum material. A lesson on geology comes alive when students can visually trace the lava flows from Olympus Mons on Mars, measuring its staggering height and comparing it to volcanoes on Earth. A physics class can experiment with gravitational slingshots by plotting their own course for a virtual probe past the moons of Jupiter. This hands-on interaction with real data moves learning beyond abstract theory and into the realm of applied, exciting discovery. It shows students that the math and science they are learning are not just exercises for a test, but are the actual tools used to navigate the solar system, making these subjects suddenly relevant, dynamic, and deeply cool. This early exposure is critical for nurturing the next generation of engineers, coders, and planetary scientists who will design the next wave of silent cartographers. Furthermore, this transparency in sharing both the process and the spectacular results is fundamental to maintaining public support for these ambitious and often expensive endeavors. When a space agency launches a billion-dollar orbiter, taxpayers are not just presented with a dry budget line item, they are invited along for the entire journey. They see the first stunning images beamed back, they follow the nail-biting descent of a lander, and they can later explore the very maps that mission produces. This open-door policy builds a powerful sense of shared ownership and collective achievement. The public doesn't just fund these missions, they experience them, celebrate their successes, and mourn their setbacks. This cultivated excitement and buy-in are the bedrock of political and social will that allows long-term exploration programs to continue across decades and changing administrations, ensuring that the silent work of mapping our future continues uninterrupted. Ultimately, this widespread outreach does more than just educate or garner support. It fundamentally enriches our collective culture and philosophy. By bringing the surfaces of distant worlds into our homes and classrooms, these maps perform a subtle but profound magic. They make the extraordinary familiar. They transform Mars from a red dot in the sky into a place with canyons, dunes, and weather. They turn the Moon from a featureless pearl into a landscape of dramatic history, marked by craters and ancient lava plains. This familiarity shrinks the psychological distance between humanity and the cosmos, fostering a deeper sense of connection and stewardship. It allows everyone, not just a select few scientists, to ponder our place in the universe, to marvel at the technologies we are creating, and to feel a part of the grand, unfolding human story that is reaching out from its planetary cradle and beginning to touch the stars. This profound capability to observe and understand environments extends far beyond the scientific and into the deeply ethical, fundamentally shaping our approach to becoming a multi-planetary species. The same orbital eyes that chart distant worlds for our future are also tirelessly watching over our home planet, providing an indispensable global perspective on the health of Earth's environment. A constellation of dedicated satellites forms a vigilant sentinel network, constantly monitoring the delicate signs of our biosphere. They track the relentless retreat of glaciers and polar ice caps with millimeter precision, measure the alarming rise in global sea levels, and map the devastating sweep of deforestation across the Amazon and other critical rainforests. Their sensors detect invisible threats: the billowing plumes of industrial pollution over cities, the subtle changes in ocean acidity that threaten coral reefs, and the atmospheric concentration of greenhouse gases like carbon dioxide and methane. This isn't merely observation, it's a planetary-scale diagnostic tool, providing the hard, irrefutable data that governments and conservation organizations need to formulate policies, track the effectiveness of international agreements, and mobilize resources to protect vulnerable ecosystems. This role transforms the silent cartographers from just explorers into guardians. their vantage point in space offering the comprehensive view necessary to steward the Earth responsibly. When we project this principle of stewardship outward, it becomes the foundational ethic for how we will operate on other worlds. The goal is no longer just to visit and exploit, but to inhabit and preserve, to practice what is known as in situ resource utilization, or ISRU, at its most sustainable core. The discovery of vast deposits of water ice, particularly in the permanently shadowed craters at the lunar poles and buried in the Martian regolith, is the cornerstone of this philosophy. Water is the oil of space exploration, but infinitely more versatile. By mapping these reservoirs with exquisite detail, we can plan missions that use local water for drinking and agriculture, but more importantly, split it into its constituent elements, hydrogen and oxygen. Oxygen provides breathable air for habitats, while together, they form a potent rocket propellant. This means a spacecraft could theoretically launch from Earth with only enough fuel to reach the Moon, refuel at a lunar depot using locally sourced propellant, and then journey on to Mars. This breakthrough slashes the monstrous cost of launching all necessary resources from the bottom of Earth's gravity well, but it also dramatically reduces the environmental footprint of each mission. Every ton of water or fuel we don't have to launch from Earth represents a massive saving in energy and a significant reduction in the atmospheric pollution caused by heavy lift rocket launches. This meticulous mapping of resources is paired with an equally detailed planning for energy sustainability. On airless bodies like the Moon, the Sun is a relentless but predictable source of power, yet its availability is dictated by the extreme length of the lunar day and night. Approximately 2 weeks of continuous sunlight followed by 2 weeks of utter darkness and crippling cold. Orbital cartography provides the essential data to overcome this challenge. By creating highly accurate maps of solar illumination, mission planners can identify peaks of eternal light, high points like crater rims that receive near-constant sunlight throughout the lunar day. These become the prime real estate for sprawling solar farms. Conversely, the maps also pinpoint the permanently shadowed regions that harbor water ice. This allows for a holistic energy strategy. Massive solar arrays on the sunlit peaks generate immense power during the day, a portion of which is used to electrolyze water mined from the nearby dark craters into stored hydrogen and oxygen fuel. This fuel can then be used in fuel cells to generate electricity during the long, cold lunar night, creating a perfectly sustainable, closed-loop energy system that requires no resupply from Earth and leaves the local environment undisturbed. This careful, data-driven approach ensures that our first footprints on other worlds do not become the last negative impressions of a careless visitor. It is the absolute antithesis of a slash-and-burn mentality. Instead, it embodies a principle of planetary stewardship where every decision, from where to place a habitat to how to dispose of waste, is informed by a deep understanding of the local environment granted to us by these robotic cartographers. We are learning from our historical mistakes on Earth, choosing to integrate with extraterrestrial environments rather than overwhelm them. This means designing settlements that have a minimal physical footprint, using local materials for construction to avoid the ecological cost of importing them, and developing strict protocols to prevent biological contamination, ensuring we don't accidentally extinguish potential alien microbes before we even have a chance to discover them. The silent, detailed work of mapping is what makes this thoughtful, sustainable expansion possible. It allows us to tread lightly, to build wisely, and to ensure that our journey into the cosmos is not a brief, destructive excursion, but the beginning of a lasting, responsible presence among the stars, leaving a legacy of stewardship rather than exploitation. This same precision that guides a rover to a safe landing or a miner to a rich deposit holds a powerful and deeply consequential dual-use potential. The incredibly detailed maps created for exploration can, with a simple change in objective, become instruments of remarkable strategic advantage here on Earth. Military and intelligence agencies around the world are among the most sophisticated users of orbital data, leveraging it for a wide spectrum of security applications that range from the overt to the profoundly secretive. High-resolution satellite imagery provides an unparalleled, persistent overview of global hotspots, allowing for the monitoring of troop movements, the construction of new military installations, or the tracking of naval vessels across the world's oceans. This constant, unblinking vigilance from orbit acts as a powerful deterrent and a critical tool for verification in international arms control treaties, as it becomes nearly impossible to hide large-scale military preparations. Beyond simple imagery, the same hyperspectral sensors that identify minerals on an asteroid can be tuned to detect the unique chemical signatures of hidden facilities or illicit weapons programs, while detailed topographic data is essential for planning flight paths for aircraft and missiles, ensuring precision strikes while, in theory, minimizing collateral damage. The security concerns extend far beyond our atmosphere, into the increasingly crowded and valuable realm of Earth orbit itself. This domain is no longer just a scientific frontier. It is a vital economic and strategic corridor, cluttered with thousands of active satellites that form the backbone of global communications, finance, GPS navigation, and yes, military command and control. Protecting these assets is a paramount concern for every spacefaring nation. This is where orbital cartography takes on a defensive, yet equally critical, role. Space agencies and military commands maintain detailed and constantly updated maps of the orbital debris field, a swirling cloud of defunct satellites, spent rocket stages, and fragments from past collisions. These maps are essential for performing collision avoidance maneuvers, nudging valuable satellites out of the path of a piece of Chinese letter debris that could obliterate them upon impact. But this monitoring also extends to watching the movements of other, potentially hostile satellites. The ability to precisely track another nation's spacecraft, to map its orbit and predict its intentions, is a fundamental aspect of modern space domain awareness, a delicate dance of observation and assessment happening silently hundreds of miles overhead. As we look toward a future of permanent lunar bases and perhaps even settlements on Mars, the principles of terrain analysis that have defined terrestrial warfare for centuries will inevitably extend to these new worlds. The first off-world settlements will be incredibly vulnerable, isolated outposts dependent on fragile life support systems and regular supply shipments from Earth. Their security will be a primary concern, and the detailed topographic maps from orbiters like the Lunar Reconnaissance orbiter will be studied not just by engineers and scientists, but by security planners. They will use these 3D models to identify natural choke points in the rocky landscape, high ground that offers a commanding field of view for monitoring approaches, and vulnerable areas like landing pads or power stations that would need to be hardened or defensively positioned. A map that shows a perfect, sheltered landing zone near a water ice deposit also reveals the most logical approach for any potential threat. This isn't about envisioning science fiction space battles. It's a practical, almost inevitable application of strategic planning for protecting critical human infrastructure in a forbidding environment, using the best available maps to mitigate risk. This inherent dual-use nature of mapping technology, its capacity to enable both profound discovery and potent conflict, presents one of the most significant ethical challenges of the space age. The very tools that allow us to peacefully explore an asteroid for resources could, in different hands, be used to guide a kinetic impactor toward an adversary's satellite. The fear is that space, the ultimate global commons, could become the next theater of conflict, a domain where wars are fought by disabling satellites to blind and cripple an opponent's economy and military on Earth below. This specter of the weaponization of space, fueled by the precise navigation that orbital maps provide, is a threat that keeps diplomats and security experts awake at night. Recognizing this danger, a growing chorus of experts and international bodies advocates for the development of new treaties and norms of behavior specifically designed for space. The goal is to foster transparency and cooperation, to create mechanisms where nations can share basic orbital data and debris tracking information to prevent accidental collisions and build trust, ensuring that the priceless data from our silent cartographers is used to safeguard assets and enable exploration rather than to aim weapons. There is a profound and often overlooked transformation that occurs when a distant, shimmering point of light in the night sky is gradually rendered into a world we can navigate, a place with named mountains, charted valleys, and known weather patterns. This act of celestial cartography does far more than fill in blank spaces on a star chart. It performs a quiet revolution in the human psyche, bridging the immense gulf between the abstract and the tangible. For millennia, Mars was a god of war, a red omen. Today, because of these maps, it is a specific location, Jezero Crater, with its ancient river delta and surrounding plains. The Moon is no longer just a celestial companion. It is a landscape with the Sea of Tranquility and the Shackleton Crater, places we have visited robotically and plan to revisit. This process of naming and knowing is a fundamental human impulse, a way of taming the unknown by making it familiar. It shifts these bodies from being mere destinations for speculation and transforms them into potential settings for human stories, for future homes, laboratories, and even communities. They cease to be merely places we look at and become places we can imagine being in. This newfound familiarity inevitably shapes our collective imagination, particularly when we ponder the ultimate question: are we alone? The possibility of extraterrestrial life moves from the realm of pure science fiction into a more nuanced space of scientific speculation precisely because we have maps. When we look at a detailed topographic model of the ice-covered ocean world Europa, with its chaotic, cracked surface, we are not just seeing a strange moon of Jupiter. We are looking at a map that suggests subglacial oceans, hydrothermal vents, and potential habitats. This allows scientists and storytellers alike to move beyond cliches of little green men and instead imagine what life might look like in a pitch-black, high-pressure ocean, fueled by chemical energy rather than sunlight. The maps provide a realistic canvas upon which we can paint more credible and infinitely more fascinating narratives about what life might be, constraining our imagination in a way that actually makes it richer and more profound. They allow us to replace fear of the completely unknown with a focused curiosity about the specifically possible. On a deeper, more philosophical level, this cartographic intimacy directly challenges some of our most deeply held notions of isolation and uniqueness. For centuries, a prevailing worldview placed Earth at the center of a universe that was largely indifferent and empty. We saw ourselves as a singular, lonely oasis of life in a silent void. But the detailed maps of Mars revealing its watery past, the charts of Titan with its rivers of methane, and the models of Enceladus with its salty plumes collectively tell a different story. They suggest a solar system that is not barren but simply different, a collection of worlds, each with its own history and potential. This doesn't guarantee that life exists elsewhere, but it powerfully implies that the conditions for complexity and perhaps even life are not a miraculous fluke unique to Earth, but might be a common thread woven throughout the cosmic fabric. This perspective fosters a sense that humanity might one day belong to a broader cosmic community, even if that community is currently one of potential rather than actuality. We are beginning to see ourselves not as isolated tenants, but as one species taking its first steps into a populated, or at least a populate-able neighborhood. This shift in perspective is what thinkers like Dr. Anya Sharma are exploring when they describe mapping as a dual act of claiming and understanding. There is an undeniable element of claiming involved. By naming a Martian mountain or a canyon on Pluto, we are planting a flag of human knowledge, asserting our intellectual dominion over that geography. But as Dr. Sharma emphasizes, the more powerful and lasting impact is one of understanding and connection. The very act of meticulously measuring and studying another world forces a humbling comparison. We see volcanoes that dwarf our own, canyons that span continents, and atmospheric phenomena unlike anything on Earth. This doesn't diminish our world, but it recontextualizes it. We are reminded that our planet is not the entire story. It is one chapter in a vast, interconnected cosmic saga. Mapping other worlds becomes a mirror that reflects our own place back at us, fostering not a sense of ownership, but a sense of participation in something infinitely larger than ourselves. This rich interplay between the scientific and the spiritual naturally spills over into our culture, providing a new wellspring of inspiration for artists, writers, and musicians. The art movement known as space art has evolved dramatically from painting swirling galaxies based on conjecture to creating breathtakingly accurate depictions of the sunset on Mars, a blue-hued event, as confirmed by Rover data, or the view from the methane lakes of Titan. Authors are writing hard science fiction novels where the plot hinges on real orbital maps, using the actual topography of asteroids to design believable chase scenes, or the precise conditions in a lunar lava tube to set up a colony's struggle for survival. These maps provide a foundation of reality that makes the stories more immersive and compelling. They give creators a shared, factual landscape to build upon, enriching our collective mythology with visions of the future that feel grounded, achievable, and thrilling. This cultural output, in turn, feeds public imagination and support for the science that made it possible, creating a virtuous cycle of discovery and inspiration that ensures the work of the silent cartographers continues to resonate far beyond the scientific community and into the very heart of what it means to be a curious, forward-looking species. Perhaps the most fascinating aspect of this entire endeavor is how the extreme demands of mapping alien worlds don't just result in specialized tools for space, but consistently spark waves of innovation that ripple back to Earth, transforming countless aspects of our daily lives. The process of creating a machine that can survive the radiation, vacuum, and temperature swings of space for a decade forces engineers to solve problems in radically new ways, and those solutions often turn out to be the exact breakthrough needed for a completely unrelated challenge back home. This isn't a happy accident. It's a direct consequence of pushing the absolute boundaries of materials science, computing, and robotics. The silent cartographers, in their quest to map the cosmos, become unintentional but incredibly powerful engines of terrestrial progress, spinning off technologies that reshape our world in quietly profound ways. Consider the incredible journey of LIDAR technology to map the precise topography of the Moon or the complex, boulder-strewn surface of an asteroid. Space agencies needed LIDAR systems that were not only phenomenally accurate but also incredibly small, lightweight, and power-efficient to fit on spacecraft with severe constraints. The drive to miniaturize these powerful laser-ranging systems for missions like OSIRIS-REx directly fueled the development of the compact, robust LIDAR units we now see on the roofs of autonomous vehicles. The core challenge is identical. Both a Mars rover and a self-driving car need to create a real-time, high-definition 3D map of their surroundings to navigate safely and avoid hazards. The algorithms first written to help a robot dodge craters on another planet are the very same ones that now help a car navigate a busy urban intersection, processing millions of data points per second to distinguish a pedestrian from a lamppost. This technological transfer turns the immense difficulty of space into a crucible for innovation, forcing the creation of solutions so elegant and effective that they inevitably find a multitude of applications back on the ground. The influence extends far beyond hardware into the very realm of thought itself, artificial intelligence. The monumental task of fusing terabytes of disparate data from orbiters, landers, and rovers into a single, coherent map of a planet demanded the creation of incredibly sophisticated AI algorithms. These systems had to learn how to correlate a radar image with a spectral scan and a topographic model, identifying patterns and resolving contradictions without human intervention. This capability for complex data fusion, perfected in the silence of space, is now revolutionizing fields like medical diagnostics. The same type of algorithm that stitches together a geological map of Mars is being used to fuse MRI, CT, and PET scan data into a single, multi-layered model of a human tumor. This allows oncologists to see the cancer's structure, metabolism, and blood flow in one comprehensive view, leading to earlier detection and far more precisely targeted treatment plans. Similarly, these advanced AI models are being applied to climate science, where they integrate data from ocean buoys, atmospheric sensors, and satellite imagery to create vastly more accurate predictions of storm paths, sea level rise, and long-term climate trends, giving societies crucial time to prepare and adapt. Furthermore, the relentless, almost obsessive pursuit of reliability for space missions establishes a new gold standard for durability that benefits every industry that depends on fail-safe operation. A circuit board destined for a deep space probe isn't just tested, it is subjected to a brutal campaign of torture that simulates decades of wear and tear in a matter of weeks. It's baked, frozen, shaken violently, and bombarded with radiation to force any potential weakness to reveal itself. This culture of extreme redundancy and rigorous testing, born from the knowledge that a single chip failure could doom a billion-dollar mission, has profoundly influenced critical sectors on Earth. The fault-tolerant computer systems that now control our power grids, air traffic control networks, and financial trading floors all inherit design philosophies that were proven in the unforgiving environment of space. The same robust sensors that measure soil composition on Mars are now deployed in industrial automation, monitoring the structural integrity of bridges, pipelines, and skyscrapers, predicting failures before they happen and undoubtedly saving lives. Even the emergency response robots that venture into radioactive disaster zones or the rubble of collapsed buildings owe their hardened designs and resilient communication systems to the lessons learned from building machines that must operate in places where no human can go to fix them. This creates a powerful and self-sustaining feedback loop of progress. Investment in the seemingly niche field of orbital cartography doesn't just buy us better maps of other planets, it acts as a high-risk, high-reward research and development program for the entire planet. A technological solution developed for a specific space problem inevitably proves its value and then diffuses into the broader economy, improving everything from healthcare and transportation to public safety and environmental monitoring. The societal benefits and economic activity generated by these spin-offs then help justify further investment in space exploration, which in turn poses new, even harder challenges that demand the next wave of innovation. The silent cartographers, therefore, are far more than just mapmakers. They are catalysts. Their work, focused on the stars, creates a constant downpour of technological advancement that elevates life on Earth, proving that the journey to understand our place in the cosmos is also, inextricably, a journey to improve it. This collaborative model represents a fundamental shift in how we explore space, moving away from a purely government-driven endeavor to a vibrant ecosystem where public vision and private innovation fuel each other. The traditional approach, where a single national agency designed, built, and operated its own bespoke spacecraft, was incredibly effective for its time but also immensely costly and slow. Missions were often once-in-a-generation events, with decades passing between major launches to the same destination. The new paradigm of public-private partnership shatters this old constraint. Agencies like NASA and the European Space Agency now act more as anchor tenants and mission architects, defining the scientific objectives and providing the initial funding and deep space communication infrastructure. They then partner with commercial entities who compete to provide the hardware and launch services at a fraction of the traditional cost and timeline. This isn't just about saving money, it's about unleashing a torrent of creativity and rapid iteration that the old bureaucratic systems simply couldn't match. SpaceX is perhaps the most visible example of this synergy in action, but the trend runs much deeper. NASA's Commercial Lunar Payload Services Program, known as CLPS, doesn't commission a single multi-billion-dollar lunar lander. Instead, it has contracted with several different companies, including Robotic, Intuitive Machines, and Firefly Aerospace, to provide regular, lower-cost delivery services for scientific instruments to the Moon. This approach embraces a calculated risk. Not every landing will be a complete success, but the overall pace of discovery and technology demonstration is accelerated exponentially. A failure in one mission becomes a learning opportunity for the entire commercial sector, and the next company's attempt is already on the launch pad, ready to incorporate those hard-won lessons. This creates a resilient and constantly evolving landscape of capability, where the failure of one mission doesn't derail an entire national program, but is merely a setback in a much broader, more aggressive campaign of exploration. Beyond simply building hardware, private companies are revolutionizing the very tempo of orbital observation. Government satellites, like the magnificent Lunar Reconnaissance Orbiter, are exquisite, one-of-a-kind observatories designed for longevity and ultimate reliability. But there's often only one of them. A company like Planet Labs, by contrast, operates a vast constellation of over 150 much smaller, simpler satellites called doves. While an individual dove's images might not match the resolution of a flagship government satellite, their strength lies in numbers and frequency. Where a government orbiter might pass over a specific location on the Moon or Mars once every few weeks, Planet Labs' flock can provide a new image of that same spot every single day. This incredibly high revisit rate is a game changer. It allows scientists to monitor dynamic processes in near real time, tracking how dust storms on Mars evolve and migrate across the planet's surface, observing seasonal changes in the polar ice caps, or even monitoring the progress of other landed missions. This turns planetary science from a series of static snapshots into a dynamic, moving picture, revealing the true, active nature of these worlds. The result of this powerful collaboration is a dramatic democratization of access to space and its data. In the past, the incredibly detailed maps produced by government missions were primarily available to a small community of academic researchers and government planners. Now, the data streams from both public and private missions are increasingly available on open-source platforms. A university student, a startup mining company, or a curious citizen scientist can access the same orbital maps that NASA uses to plan its rover traverses. This openness fuels a virtuous cycle. It allows a wider pool of talent to analyze the data, often spotting patterns or asking questions that the core mission team might have missed. It enables small companies to develop new applications for the data, from creating educational video games set on accurate models of Mars to developing software tools that automatically flag new impact craters or geological anomalies. By breaking down the barriers to entry, these partnerships are ensuring that the benefits of orbital cartography flow to society as a whole, sparking innovation and engagement in ways that a closed, government-only program never could. This spirit of global partnership is perhaps the most natural and powerful force in space exploration, because the universe itself knows no borders. The challenges of mapping distant worlds are so immense, and the costs so astronomical, that no single nation can realistically hope to tackle them alone over the long term. This practical reality has fostered an environment where collaboration isn't just encouraged. It's essential for meaningful progress. When a satellite operated by the European Space Agency detects a fascinating geological feature on Mars, that data is rarely kept in a proprietary vault. Instead, it's quickly shared with scientists at NASA's Jet Propulsion Laboratory, who can then task their own orbiters to take a closer look with different instruments. Researchers from the Japanese Space Agency JAXA might analyze the spectral signature, while their counterparts in the Indian Space Research Organization contribute topographic data from their own missions. This isn't a series of isolated efforts, it's a constant, flowing conversation between nations, all contributing their unique pieces to a single, ever-expanding puzzle. The result is something far richer and more complete than any one country could ever produce, a truly holistic understanding of a planet, built from a global pool of knowledge and expertise. This collaborative spirit is made tangible through ambitious, multinational projects that would be impossible for any single nation to execute. The Lunar Gateway, a planned space station that will orbit the Moon, stands as a perfect example. This isn't a NASA station, it's a global outpost. The United States is providing the power and propulsion element. The European Space Agency and the Japanese Space Agency JAXA are collaborating on a state-of-the-art habitation module. The Canadian Space Agency is contributing its renowned robotic arm technology. Even the Mohammed bin Rashid Space Center in the United Arab Emirates is involved, providing an airlock for the station. Every aspect of the Gateway's design, from its orbital path to the placement of its docking ports, is informed by the collective mapping data provided by all these partners. They are building from a shared atlas, ensuring that this international hub operates seamlessly and safely for all its users. This model pools financial resources and distributes technical risk, but more importantly, it creates a shared stake in the venture's success, binding nations together in a common, peaceful objective that rises far above terrestrial politics. However, weaving together the efforts of so many different countries, each with its own political mandates, technical standards, and cultural approaches to problem solving, is a monumental exercise in diplomacy and compromise. It requires a relentless focus on creating interoperability, the ability for different systems to work together seamlessly. This means agreeing on common data formats so that a map generated by a Russian instrument can be instantly read by American software. It involves standardizing communication protocols so that a Japanese rover can relay its findings through an European orbiter to a ground station in Australia without a glitch. These might sound like dry, technical details, but they are the absolute bedrock of international cooperation. Without them, the shared mission collapses into a cacophony of incompatible systems. Reaching these agreements demands long hours in conference rooms, with engineers and diplomats patiently working through countless technical specifications, often having to sacrifice a slightly better, proprietary solution for a good, universally acceptable one. This process is a powerful testament to the shared goal, proving that when the objective is compelling enough, like mapping a new world for all humanity, nations can find a way to align their efforts. The ultimate success of these international mapping endeavors demonstrates a profound truth, that the silent cartographers can act as a powerful unifying force on a planetary scale. In a world often divided by conflict and competition, the shared mission of understanding our cosmos provides a rare and valuable platform for peaceful engagement. Scientists and engineers from nations that may have deep political disagreements on Earth can work side by side on a mission to map the clouds of Venus or the icy shell of Europa, united by their common curiosity and respect for the scientific process. This doesn't erase those terrestrial conflicts, but it builds a separate channel of communication and trust, creating a community that operates by a different set of rules governed by evidence, logic, and the shared awe of discovery. This collaboration proves that our greatest achievements are rarely the product of isolation and competition, but of pooled knowledge, shared ambition, and the recognition that some frontiers are simply too vast for any one flag to claim. The maps they create together become more than just navigational tools. They become symbols of what we can accomplish when we choose to look outward together as one species. But the work of these silent cartographers doesn't end with simply documenting what is. Its most powerful application lies in projecting what will be. This is the revolutionary leap into predictive mapping and simulation, where the static atlas of a world becomes a living, breathing forecast of its future. Imagine having a weather app not for your city, but for an entire planet, predicting global dust storms on Mars months before they begin to swirl, or modeling the precise wobble of a distant asteroid a century into the future. This is no longer science fiction. It's the critical next step in orbital cartography, transforming it from a descriptive science into a prescriptive one, allowing us to not just understand these environments, but to outthink them. This predictive power is built upon an immense foundation of historical data, the painstakingly gathered observations of decades of orbital surveillance. To forecast a Martian dust storm, scientists don't start from scratch. They feed sophisticated climate models with years of detailed information on atmospheric pressure, temperature gradients, wind patterns, and solar radiation intensity, all meticulously recorded by orbiters like MAVEN and Mars Reconnaissance Orbiter. These models can identify the subtle precursors to a planet-wide event, perhaps a specific pattern of warming in the southern polar region that has, in the past, consistently triggered a cascade of smaller storms that then merge into a global monster. By recognizing these patterns, the models can provide mission planners with an early warning system. This allows them to command the rovers on the surface to hunker down, conserve power, and enter a safe mode before the first winds even begin to blow, ensuring these priceless robotic explorers survive an event that could otherwise coat their solar panels in a fine, power-killing dust and end their missions prematurely. The applications extend far beyond weather into the very fundamental mechanics of celestial bodies. Consider the challenge of landing on a small, fast-rotating asteroid like Bennu. Its irregular shape and weak, lumpy gravitational field cause it to spin and wobble in complex ways. Trying to rendezvous with such an object using only a static map would be like trying to jump onto a spinning carousel while blindfolded. Instead, mission planners used the detailed shape model created by the OSIRIS-REx spacecraft to run thousands of computer simulations. They modeled the asteroid's rotation, its thermal properties, how sunlight heating its surface causes it to spin faster or slower over time, and even how it might shed material into space. These simulations allowed them to predict the asteroid's exact orientation and gravitational environment years in advance, enabling them to program the spacecraft's autonomous navigation system with the precise knowledge it needed to make those critical, real-time adjustments for its delicate touch and go maneuver. The map wasn't just a picture, it was a dynamic, physics-based simulator that de-risked the entire mission. This forward-looking approach fundamentally changes our strategic planning from a reactive posture to a proactive one. Instead of simply responding to challenges as they arise, we can now use these predictive models to game out countless scenarios long before a mission ever launches. Planners can simulate the long-term erosion of a potential landing site on the Moon to ensure it will remain stable for a decade-long habitat. They can model the shifting illumination patterns at the lunar poles over a full 18-year cycle to optimize the placement of a solar power farm that will receive near-constant light. For future human missions to Mars, these simulations will be indispensable for selecting base locations that are not only rich in resources, but also situated in regions statistically less prone to the most severe dust storms, or where the soil composition is ideal for radiation shielding. This ability to peer into the future transforms orbital cartography into the ultimate decision support tool, turning what was once a dangerous gamble into a carefully calculated endeavor. As our computing power continues to grow at an exponential rate, so too will the fidelity and scope of these predictions. We are moving towards exascale computing, systems capable of a quintillion calculations per second, which will allow us to run simulations of breathtaking complexity and scale. Future models might not just predict a global dust storm on Mars, but simulate it at a resolution of a few meters, accurately forecasting how the dust will settle on every hill and valley, and how it will affect the performance of every individual solar panel on a rover. We could create a digital twin of an entire planet, a perfect virtual copy that evolves in real time alongside its physical counterpart, allowing us to test ideas and interventions in the simulation before ever committing to them in reality. This isn't just about avoiding danger, it's about identifying opportunity. These powerful predictive tools will allow us to optimize every aspect of our off-world existence, from scheduling supply launches to coordinating the activities of robotic swarms, ensuring that humanity's first steps into the cosmos are taken not with trepidation, but with the confident stride of those who have already walked the path 1,000 times in simulation. This incredible wealth of data, this living atlas of the solar system being compiled by our silent mechanical scouts, would hold far less power if it were locked away in a vault, accessible only to a select few. The true potential of orbital cartography is only unleashed when its maps are set free, made available to anyone with curiosity and an internet connection. This philosophy of radical openness transforms these detailed surveys from proprietary tools into a global commons, a shared foundation upon which an entire future can be built. Initiatives like NASA's Planetary Data System, or PDS, are the pillars of this open access movement. This isn't a curated gallery of pretty pictures. It is a vast, meticulously organized digital library that provides completely free access to the raw, unprocessed data streams from decades of missions. Every image from the Mars rovers, every laser altimeter reading from the Lunar Reconnaissance orbiter, every spectral scan of an asteroid, it's all there for the downloading. This commitment to transparency is a powerful declaration that the exploration of space is a human endeavor, not a national one, and that its discoveries belong to everyone. This democratization of data shatters the old barriers to entry, empowering a new and incredibly diverse wave of participants in space exploration. A university student in Nigeria can download the same datasets as a professor at Caltech, using them to train their own machine learning algorithms to search for new geological features on Mars. A high school science teacher can pull high-resolution maps of the moon into their classroom, allowing students to conduct their own virtual field trips to the Apollo landing sites. Perhaps most excitingly, ambitious startup companies no longer need to raise hundreds of millions of dollars to launch their own mapping satellite just to scout for resources. They can instead mine the existing public data from government missions to identify promising asteroids for mining or ideal locations for a lunar hotel, building their business plans on a bedrock of free, verified information. This levels the playing field in a way that was unimaginable just a few decades ago, turning what was once the exclusive domain of government agencies and elite institutions into a playground for global innovation. We are now seeing the rise of the citizen scientist, where amateur astronomers and enthusiastic hobbyists regularly pore over public data, sometimes making genuine discoveries, like identifying new impact craters on Mars or unusual surface features on Ceres that were missed by the overworked professional teams. This collective brainpower, unleashed by open data, dramatically accelerates the pace of discovery. However, this flood of information brings its own set of monumental challenges. The sheer volume of data being produced is growing at an exponential rate, threatening to overwhelm the very systems designed to share it. A single modern orbiter can transmit terabytes of data back to Earth every day. Storing, organizing, and processing these colossal datasets requires massive and ever-expanding computational infrastructure. The problem is compounded by issues of standardization. Different space agencies and even different missions within the same agency often use unique file formats, data structures, and calibration protocols. Making a radar map from a European Space Agency satellite seamlessly align with a laser altimetry map from a Japanese mission and a spectral image from NASA can require a Herculean effort of data translation and reconciliation. Without consistent standards, the dream of a perfectly integrated, seamless solar system map remains just out of reach, as researchers waste precious time converting files and correcting for inconsistencies instead of making new discoveries. Addressing these challenges is critical to ensuring that the benefits of this silent revolution are shared as widely and equitably as possible. The goal is to build a truly interoperable system, a sort of cosmic internet where data from any source can be easily found, accessed, and combined with data from any other source. This requires a global commitment to developing and adopting common data standards and metadata protocols, essentially agreeing on a universal language for describing planetary information. Furthermore, the next frontier is moving beyond simply providing raw data to offering processed, analysis-ready datasets and powerful cloud-based computing tools. Instead of forcing a student to download a 10-terabyte dataset that would overwhelm their laptop, a portal could allow them to run their analysis on the server where the data already resides, seeing only the results. By investing in this next-generation data infrastructure, we ensure that the door to participation remains open not just to those with the biggest budgets or the most powerful computers, but to anyone with a good idea and the passion to pursue it. This inclusive approach is what will ultimately fuel a vibrant and sustainable spacefaring society, where the maps to our future are drawn by the many, not just the few. So as we bring this journey to a close, it's worth pausing to reflect on the profound shift these silent cartographers represent. They are not merely tools we send into the void. They are the very embodiment of a new philosophy for exploration, one built on preparation, foresight, and profound respect for the challenges that lie ahead. This isn't the reckless rush of earlier eras, but a deliberate, meticulous, and deeply intelligent approach to opening the cosmos. Every contour line on a map of Mars, every spectral signature from an asteroid, every hazard identified on the Moon is an act of care, a commitment to ensuring that when humanity finally takes those next great steps, we do so not as blind wanderers, but as informed guests, ready to engage with these new worlds thoughtfully and sustainably. The legacy of this work will echo for centuries. The maps being drawn today are the foundational charts upon which the entire edifice of our spacefaring future will be built. They are the blueprints for the first off-world cities, the prospectuses for the first interplanetary commerce, and the inspiration for the art and culture of generations who will come to see the solar system as their backyard. These silent scouts are writing the first chapter of a story that has only just begun, a narrative of a species learning to live among the stars, and they are ensuring that it starts not with a stumble, but with a confident and well-prepared stride. Their work guarantees that our greatest adventures are still to come, and that they will be built on a foundation of knowledge as solid as the ground we hope to one day